Good afternoon. Welcome to lectures 55 and 56 on thermodynamics of materials. Today, at the very beginning, we'll just brief what we discussed last day, or the salient points or essential points. So, essential points from the last class, quickly. Essential points from the last class. What are the points? One by one. First is number one. We had this relation Gi bar minus Gi0 is RT ln activity AI. Second is delta G is delta G0 plus RT ln Q. And third is maybe these two, okay, is delta G0 is minus RT ln K. These three things we actually found last day, and also we okay. This is, remember, this is this and this. This 1 and 3, these two are these two relations are the most important ones in chemical metallurgy, in chemical thermodynamics, maybe in chemical thermodynamics, or chemical reactions, involving chemical reactions, this two. And also, so you can draw this line, and I'm helping you how to remember the second one from the first one. Second one, you see clearly, see delta Gi bar corresponds to delta G. Delta G is nothing but Gi bar product minus Gi bar reactant last day. 3 Gc bar minus Ga bar, etc. So this corresponds, and this goes to the other side. Gi0 corresponds to delta G0 as product reactant for the chemical reaction, and RT-ln activity product by reactant is Q. Study, okay, so easy, and this is also coming from this. Now what else actually I wanted to discuss? One point first of all, one confusing point I want to take up once more. Last day I discussed though, but be careful. One confusing point is this, okay? What is this? Condensed phase. In condensed phases, what I said, activity. Condensed phases. What is the AI? Is, remember, as I write always, as if as a ritual, Fi by Fi naught, then I write is as Pi by Pi naught. Remember this, identify this Pi naught. Pi naught is this, say for example, Eg, say iron pure, iron manganese solution. You apply this. The question is how to get the activity of manganese. Okay, this, what is this? This is actually, write this. This is saturated vapor pressure. Saturated vapor pressure. Vapor pressure of I. Okay, liquid or solid. Liquid or solid. Or pure I, right? Pure I. Right, pure I of vapor pressure of pure I, pure I. And this is the vapor pressure of I in impure state. I take an example. So pure I means, suppose I is iron, as I've said. Say, okay. Easy say I is iron liquid. So what is this? Pi, P liquid iron vapor pressure, saturated vapor pressure of pure liquid iron. This is actually typically these values Pi, P iron 0, typically much less than 1 atmosphere. Note this. Note, much less than 1 atmosphere. This is one thing. This is the vapor pressure. Now, very good. Now, question is, suppose when we add manganese, so this is I is in impure state. Say impure state, impure iron is what? Contains iron and manganese. Now, question is, what is the vapor pressure? Pi is then P iron is what? As you know, P iron must be less than vapor pressure. This is, so for example, say I can have much less than, say just take an example, say point, yeah, let me write, say, say 10 to the power minus 3 atmosphere, say much less than, there is ball typical. Achha, now PAP is, it is less, suppose PAP is when a manganese is added 10 to the minus 4 atmosphere, less. Then what is the activity of iron? Tell me, what is the activity of iron? As you see, I is the iron. PAP by, good. PAP not substitute. Find a value mathematically, you have more impact on this. So it is 10 to the power minus 4 divided by 10 to the minus by minus 4 minus 3 is 0.1 activity. No unit. Okay. See, take a note here. Pi 0 is this. But consider now, in contrast, in the case of nitrogen, in the case of gas phase, of a gaseous species, say nitrogen. Again follow, what is the first line is activity of nitrogen. What you write is also M nitrogen by M nitrogen 0, and you write again it is what? This is no more, this is actually pressure. Okay, fugacity and pressure actually separated by this. Okay, now there is actually, so pressure nitrogen is, you can approximate. What is this? My question is, the confusion is here. What is P into 0 value? See, P into 0, remember this 0 is what? Standard state 0. This 0 is what? Saturated or equilibrium vapor pressure. Saturated, another name is equilibrium. Equilibrium vapor pressure. Saturated, so this superscript 0, nothing to do. Vapor pressure of what? Of pure I. And this is in standard. Liquid iron standard. This vapor is not standard. Vapor is a gas. For gas, what is the standard state? 1 atmosphere, sir. So we'll apply this for gas nitrogen. What is this value? This is 1. So this leads to PN2 only. So you know this room, actually I asked you last day, what is the activity of nitrogen? A partial pressure of nitrogen, which is 0.8 roughly. So this will be the answer here in this room. This is 1, but this is typically not 1, in fact much less than 1. Vapor pressures are not large actually until boiling point. These are the things. But then you say, sir, why is this 0? No, this is actually standard nitrogen. This is the vapor pressure of standard iron. Standard liquid iron. What is that, sir? Pure iron. So here again, so jot down, recall What is the standard state? May helpful. Clearly, what is the standard state for? Standard states. For solid liquid, standard state. Solid liquid, what is the standard state? Tell me. Standard state, pure state at 1 atmospheric pressure. You write that. Pure state and at 1 atmosphere pressure. This is important. Okay, important means, okay, you have to mention at least at the temperature of interest. This you studied for solids, and for gases, again, right? It is again pure, okay, pure gas. Let me remove this. This is no longer pure gas at 1 atmosphere at the temperature of interest. Actually, this is actually I could have explained it if it is not pure mixture. That is also same result, same. Okay, but 1 atmosphere mass. Temperature is not mentioned, any temperature. Standard state has not any temperature. It can be 290, 300, 400. Okay. So now one actually question is, it is actually difficult for you to accept this last day. So I'm picturing this iron liquid I'm taking. You have some difficulty. First you have overlooked this, but I have a duty to explain this iron liquid. Happy? And you have iron vapor on the top of this. Equilibrium at the temperature, thermostated, as you know, thermostated temperature T. Liquid means it is above the melting point of iron, obviously 1600 degrees centigrade certain value. Okay, this what is the pressure? P0, what value I have considered? Right, use this since I have already considered is 10 to the minus 3 atmosphere, say, just arbitrarily. Then what is the picture, sir? This is the equilibrium picture. What is the pressure? Pressure is on the top for PAP. P is 10 to the 1, sorry, right? 10 to the minus 3. Sorry. 10 to the minus 3 atmosphere. Okay. This is the equilibrium state. Now, so what is this pure state at 1 atmosphere pressure? Here's the difficulty. You might say, this iron is in the pure state, the standard state. I said, no, the standard state. Okay, this iron liquid is at standard state. Because standard state has a temperature of interest. Temperature is T of interest. So, but another thing stated 1 atmosphere pressure, sir. These irons are at under what pressure in the figure? 1 is where? 10 to the power minus 3 atmosphere, it is exposed to its own vapor pressure, sir. No other gaseous species. So how it is a standard state? I have already said the iron is in the standard state. It is substituted vapor pressure. Pure means pure I have considered, and in fact I will consider as standard, but explanation is required. Sir, why 1 atmosphere may be ignored? I will show this. This is the picture, 10 to the minus 3. So what is the vapor pressure of iron liquid? Is perfectly this answer if it is happens to be correct data, but this is the picture. For water also, for water 69 degrees centigrade other day is what? 69 degrees, what is the value? 0.3 atmosphere. That picture. Now at 1 atmosphere, so how will show this? If I make it 1 atmosphere, what will happen? You know, this vapor will collapse. Condensation will take place and it will be iron liquid only. So how will you show this? There is a possibility. This I am saying 1 atmosphere have to satisfy quickly. Iron liquid 1 atmosphere. This is not 1 atmosphere. This is not right here. This is not. This will be clumsy. So let me write. How will you make it 1 atmosphere? Take argon gas to fill in. Argon gas. Balance and Fe. Sorry. Okay. Right. Argon gas, Fe vapor, and Fe liquid. This is the picture. So this is actually say under typically 1 atmosphere. So question argon. Say argon has a giant share. So 1 atmosphere. This is a 10 to the minus 3 of total argon pressure. Under 1 atmosphere argon, what is the vapor pressure, sir? This question comes. Answer is we know under 1 atmosphere vapor pressure does not change much. This is the interesting. Pressure I say is not much dependent on vapor pressure is not much dependent on external pressure. Dependent, but for this small one in the regime of 1 atmosphere, it is not much. So I will write here still PAP 0 vapor pressure is still close to close to what value? Tell me. 100%. So as if close to me, I tell you, it will slightly increased. Increase pressure will increase. It cannot stop it. Thermodynamically, you cannot stop it. Close to me, slightly greater than, right? Slightly greater, so that you have a greater feeling. Slightly greater than 10 to the minus 3 atmosphere. And we ignore this effect. We ignore this. That's why pressure we don't consider. We consider this picture. This picture for the PIF. Okay, sure. So effect of pressure is ignored. But a large change in pressure will cause measurable change. Large means 1,000 atmosphere. You know, if you, by application of pressure on the condensed space, effect of pressure is small. But if you keep on increasing the pressure to a large value, then this significant changes occur. In fact, graphite becomes diamond by the application of pressure. You know, okay. This is actually is obtained actually in the in mines actually. Then diamond is produced at high temperature and pressure. Application of pressure. These are example I will take up that graphite will be converted into diamond for the application of pressure. Moreover, I can tell you the phase diagrams. Okay, eutectic diagram is drawn actually. All these phase diagrams are drawn, which is not written there. Should have been written in every books, everywhere, every teacher at 1 atmospheric pressure. The melting point that you so AB, have you ever drawn any phase diagram? So a melting point AB, that is normal melting point, is under the 1 atmosphere system. Change to 2 atmosphere, melting point can never be there. Iron melting point is never 1593 degrees centigrade if the pressure is the 2 atmosphere or 3 atmosphere. And if you change it enormously, then this eutectic diagram will change. Okay, will convert into peritectic diagrams. So much effect of pressure when it is tremendously high. For such a small change, it is ignorable. So in the domain of this 1 atmosphere, whether this figure or that figure, I will accept this. This is pure iron, is actually, and liquid iron is accompanied by its vapor pressure. And still, and purities matter. Purity matters. If you make it impure, what will happen? What will happen? Tell me. 10 to the minus 4. Even less, it may make it more and more impure, add more and more manganese, 10 to the minus 5, 10 to the minus 6, and so on. This is the whole story. So I think this requires some discussion. I have actually take up talking about this. Next is, I'll remove all these things. Better. Okay, next point is, last this, what I said, Q less than. So different alternative statements of the second law. So I will draw this. Today I will draw this. Okay, what is this? Finish this. Okay, this finish this diagram. Acha, by the way, quickly another point. Another point in passing. Another point to be noted in passing. If possible, I will give you effect of pressure on Gibbs energy as well as vapor pressure, all these problems. One problem I will take up. Another interesting point. What I last class referred to the last class. What I got, you recall this DGPT. Tell me, DGPT. I wrote as prime for extensive property. I don't mind. It is actually DG. G is what? It is what a bit. DGPT is delta G dn. Delta G dn. Okay. Now I tell dn is what? Just a little bit recollection. A plus 2b quickly. What is this? Minus dna. As you wrote this, minus half dnb is 1/3 dnc is dn like this plus plus dn positive, positive, okay. Now this we are reached, DGPT. Now applying this recall, now involving electrochemical work in the system, involving electrochemical work in the work which is non-mechanical work as you call it, dw prime in the system. What is that statement? The second law, DGPT second law is what? You know, zero. This is our strength. This side is coming. Then we infer from, since it is zero, what is the equilibrium condition? Delta G is zero. Last day done. Because Dn cannot be zero. Dn is a positive quantity, positive or non-zero quantity. So this is done. Delta G is zero for equilibrium, less than zero, based on the second law. If you might write second law, just here in terms of this DGPT, I write DGPT, but it's G prime actually. The way I wrote you previously, minus dw prime. Recall this. Is for reversible, is sign for reversible equilibrium, etc. This you remember. And when dw prime is zero, no non-mechanical work in a chemical, simple chemical reaction. Where is the non-mechanical work? Zero. This simplifies to, sir, less than zero. That's why DGPT is zero. And hence Dn non-zero, delta G is zero is the equilibrium condition last day. And this is negative, hence delta G is negative, last day's condition. So I gave you the condition. This is the original condition. I have a different thing in my mind today, not previous, not that I am discussing. Okay. Electrochemical work I am involving. Okay. Now this, so then DGPT is what? DG prime PT is I am writing for you, like call it equation 1. Please. DGPT is what? Minus, write this. dw prime for reversible condition. For reversible condition. What is this? Reversible condition means dw is non-mechanical electrochemical work. This electrochemical work shall be like this. Suppose I consider electrochemical, I have written there. So what is the electrochemical work? You know, it is actually the charge that is passed over a potential gradient. That is electrochemical work. PB work, you know, PdV. This is also charge passed over a potential gradient. So charge times potential gradient. So I am writing charge times simply electrical charge times potential gradient. Potential gradient, write this way. What is the, for this dw prime differential, what is the charge that is, you know, Faraday is the 1 Faraday, 96, okay, 1 Faraday is carried by 1 gram coulomb, just 1 gram coulomb, okay, is quantity, is charge is carrying 9650 coulomb. What is this? So Dn gram equivalent, I write in Dn already used, Dn prime times I am writing, you take up this first of all. This is the standard equation for electrochemical work. Dn prime Fe. Why? Farad is gram equivalent. It is number of gram equivalent, right? Number of gram equivalents, you know this, not bad. It is coulomb per gram equivalent. What is Faraday? Charge per gram equivalent. As a result, cancel. Number of gram equivalent and per, okay. So coulomb remains, and E is what? Potential difference, potential or potential gradient, okay? Potential is volt actually, volt, potential gradient, volt. So you coulomb volt, it will be joule, okay? So this. So now if you actually, if it is this minus this, then what you call it equation 2, quickly. So equating from 1 and 2, equating from 1 and 2, delta G dn, left hand side is same, is minus dn prime Fe, or delta G is what, sir? Oh, dn prime, to change from dn prime, write this. Number, so minus dn prime by dn Fe. This gentleman is known as, you know, number, dn is the number of gram moles, number of moles. dn is number of, changing the number of moles though, number of moles. So change number of moles, number of gram equivalents in number of moles. This ratio means how many gram equivalents are there in 1 gram mole, you know, molecular weight and equivalent weight. How many gram moles are there in one gram equivalent? What is the answer? That gives number of electron. That gives actually. Say for hydrogen, okay, 1 gram mole sulfuric acid, 1 gram mole is 98 gram, and gram equivalent is 98 by 2. So when it is electrolyzed, how many electrons are involved? 2H plus 2 electrons. So 2. So 2 is coming actually, it is 98 and 49. So it is number of, this is minus n. This n actually, I think number of, this n is the number of electron. N is number of electron. This is your famous relation. Number is same as number of grams. So right is actually right here is number of, it will help you, number of gram, number of gram equivalent, write this, per gram mole. You refresh this mole and gram mole. This is one thing I wanted to show additional proof. This is your electrochemical relation. Okay, this is used in, this relation is used. Delta G is minus NF is a famous relation in, important relation in EF cells. Relation used in EF cells. This much I will say. I will not go beyond this. Next point is what? Now actually I tell you. So this part is over. Just keep on writing while I start the next one. This means I continue with this. So let us continue with the last day's class. Now take up today's class. Okay. Okay. Let us continue with the last day's discussion. Now continue with the last day's discussion. Now continue with the last day's discussion. Where we are last day? Where what I said? Recall, I said three. What is the equilibrium condition? Is what? Like this. Remove this. Remove this. Remove this. This I said. Okay, last day. dgpt less than equal to 0. dg prime pt, or what I said? dg prime pt by dn is less than equals to 0. This is nothing but, that is delta G less than equals to 0, or this gives rise to G prime pt is minimum. This much, this I will say. Today I will show this minimum. I will draw a graph and I will show this. What is this? Everyone saying that free energy is minimized at equilibrium. And like stable state, equilibrium state, they say. So I am drawing this. Reference, consider the reaction, consider last day's reaction, consider the reaction. A plus 2B is 3C. Quickly, quickly. That is, from this also you get what? Q less than K. Okay, this you remember last day. This I discussed, all discussed actually. This is second law, right? Yes, this is second law. Starting from the second law. So I am plotting G prime PT. So I am writing this side CO plus half O2. Oh, I am sorry. I am very sorry. A plus 2B. This 3C. And I'll also write that A plus 2B 3C. What is this? Minus, please write, minus DNA is minus half DNB is plus 1/3 DNC. Write all this. Is DN that you wrote. I am plotting here, see, A plus 2B, N moves from 0 to 1. And likewise NC is 0 to 3. N is moving from 0 to 1. I am plotting G prime PT. You follow this. The minimum I am showing. This is the minimum. Just dotted. This is how I start from this side. The reaction moves and stops here. Or if you start from this side, this stops here. This is the minimum. This is which curve? G prime PT versus N curve. So you please consider 3 points. P, consider point Q, consider another point R. 3 points. You take a look. DG follow. What is this? I'm writing this is the free energy is minimum. So you write this is actually the minimum. Minimum. Who is minimum? G prime PT attains a minimum when plotted against N. What is N? N is actually 1/3 NC. You may take a look. As the way we have placed this. So this is the okay. This is Q, and this is also you can write on the. This is the equilibrium as well. This is the equilibrium state. Equilibrium state. And this zone I write you non-equilibrium. Actually, rather non-equilibrium I'll explain you. Actually, right, non-equilibrium, no problem. Non-equilibrium. More important is this is spontaneity. And this side is also non-equilibrium. This side is right non-equilibrium and right impossibility. Impossibility with respect to the reaction. Consider A plus 2B going to 3C. So you start from here. So you can see on the what, just consider one point P. What happens here? See, delta G is what? Equilibrium state minima. You write here also write delta G is 0, and right here this side you write delta G is this side right delta G non-equilibrium accompany negative, and this side right non-equilibrium is delta G is positive impossibility. Okay, non-equilibrium we don't say you say impossibility. So P at this point P. Okay, see if you take a slope, what happens? Take a slope. Slope. What you see? Slope is positive or negative? Slope is dg prime pt as you see. Sorry, by dn is negative. You clearly see. And you at r, what is the slope? Slope at r is again positive. Slope at P. What is the name of dg prime pt by dn? Is same as delta G. Here I wrote a moment ago. I will check this in dg prime pt. Recall this. I write somewhere dg pt. A moment ago I wrote this. I shall write dg prime pt. This is important. Delta G dn. That means dg prime pt by dn is delta is as good as delta G. Delta G negative. You see negative slope. So negative means spontaneity. Delta G negative, recall. Delta G, right? Negative means spontaneity. And equilibrium means equilibrium. What is the slope? 0. Here, minima 0. And what is the slope? Positive. So impossibility. So reaction starts from here and stops there. This is the message, okay? And under what condition you have write? You may write, okay? Additionally, PT or superficially style constant P, constant T, right? Constant PT, right? Nicely constant P, constant T under. Good boy. So this is the picture graphical presentation, right? Graphical presentation. What I am doing? Graphical presentation of spontaneity, equilibrium, and impossibility. Okay? With the help of, tell me, with the help of G prime PT versus N plot. Happy? This is the message. Okay? This you see. Okay? This is the message. Now, what I wanted to tell you, this is DGPT. Now, okay, this is over. Okay, good. This is okay. If I have missed any point, I will come back. This is over. This is non-equilibrium, equilibrium. This is equilibrium minima. as a equilibrium and minimum coincides right here. Equilibrium, minimum, free energy minimum where written here. Free energy minimum is the minimum where corresponding to G is minimum means when, right here, right, when dg prime pt by dn, sorry, is minimum for when, right, dg prime pt by dn is 0. When it is 0, it is minimum. Okay, less than 0 for spontaneity. So it is for equilibrium. Equal sign for equilibrium, hence minima. So you see, minima, the minima equilibrium coincides. Now another point, this part is over. Now another question. Now can we so criterion is what? Criterion of spontaneity. Delta G negative is one, and another is slope negative. Okay, this is another one. Okay, delta PT dn is 0 when delta G minimum is okay. Now we consider another thing. Can we consider, actually, one thing I tell you, this delta G, tell me again, come back. Then here, what is this value? Negative is right here also delta G. See, follow. Negative, this is what? Negative. So minus 40 negative, minus 40, minus 20, minus 10, minus 5, minus 3, 0. So this domain is delta G negative domain because slope is negative, which is delta G and non-equilibrium and spontaneous reaction. So this, and then it is 0. And this side, actually, again, you see, you have what I've written. This is delta G is 0 for this point. Okay. Now, question is, you are using delta question confusion. So this I raised myself. So delta G refers to a single state. Refers to a single state. We are used to consider delta G for a change in state. So we are used to consider delta G for a change in state, like 1 to 2 are, and delta G there indicating delta G is G2 minus G1, all such things. Delta H, delta right here, like delta H, delta U before, like delta H, delta U. But today delta G, which state? Yeah, delta G. So at a point, and that is delta G. So how this I have discussed, I should not repeat. Delta G is what? Delta G is what? Remember, all reaction under the reason. Delta G is what? Right? Once more. Right? Tell me. 3 GC bar anytime minus GA bar plus 2 GB bar. Happy? Acha. Is okay. Delta G. That is in short, sigma G product minus sigma G reactance. Please write this. Another thing I will ask you, delta G is this. What else I will tell you here? Delta G is this. This you recall this. Delta G is 3 GC bar minus GA bar plus 2 GB bar. Another point I write here. This will be helpful. Just since I remember this, I told you that remember always. What is G prime? Anyone? G prime? Yeah. What is the G prime? There is some free energy. I am plotting free energy. I have no idea. I may see. I draw some qualitatively. But I have some idea what is G prime. What is G prime here? Free energy of the system, which I start with here A and 2B. The way I have drawn A and 2B, and it reacts, produces, and I have considered the whole range as if it has converted to 3C, which is impossible because it will stop in the middle. But I have drawn the curve. So, for example, one point, if I can answer that this is how we have obtained this point, then we can answer for all points, explain all points. So, how this G prime here obtained here? This I am going to write there. So, what is it? Tell me, what is the G prime? G prime is the total free energy of the system. What is this? I told you 3 things. So, inside in the container, consider container A, 2, B, 3, say playing inside the container. Then it is NA bar, remember, plus NB GB bar. This never, I told you, never forget. NC GB bar. Never forget. This you never forget. This you never forget. Not forget. Also this. So I don't know which you can afford to forget. So this is G prime. So what you will say? So G prime is what? Number of moles. You start with 1 and 2 as if for ideally, and so you get certain number of moles. What has happened? Suppose you start with 1 and 2. 1 is decreasing, B is one is less than 1, say 0.8. 1 is 0.8 here. Now what is the B? B was 2. It is twice as much. Stoichiometrically 1.6. And what is C, which was 0 here, has been 3C. 3C, it is 0.6. 0.6 here. 0.6 no? 1 is reduced to 0.8 means how many moles of A is removed? 0.2. If it is 0.2 removed, according to the stoichiometry, it is 3 times as much. So this is how things changes. And here when it is A and B are 0, means all 1 mole of A is totally disappeared along with 3 moles of B. How many has been produced? 3C. This is the actual. So how will you get this? Then you will say, sir, Na, whatever, sir, Na, say 0.8, etc., etc., 0.6, etc., etc. G bar, G bar is what? G bar is what? So G bar is a function of composition. Okay, G bar is GA0 plus RTL and A. In principle, G bar is GA0 plus everything. That is, you cannot afford to forget. GA0 plus RTL and activity. What is activity? Activity for gases is nothing but partial pressure. Partial pressure, deals with moles. Partial pressure is about moles. Mole fraction time total pressure. Total pressure is PR, say 1 atmosphere high, fixed on the top. Mole fraction, number of moles by total number of moles. So you know this. So Gi bar is knowable if G0 is known. Absolute value is not known, but we have solved the problem through the delta, and we have actually good, nice relation here. We can solve all problems that will take up soon. Okay. So this way you can do. Now question is, so at this state, delta G, you understand. When I write delta G, you said, sir, at a state, and the many questions, at least the initial question I will consider whether reaction is feasible under this condition, any given condition, say 2 moles of A, 3 moles of B, 4 moles of C, and answer this. So, sir, any condition, sir, delta G, only one state, delta G, the G of product minus G of reactants, they are finished. Can you tell me why this value has changed to this value? Following this, you can answer easily. Sir, G prime here cannot be G prime there. Why? What is the reason? Yes, sir, Na and B and C in continuous change. Continuous change, all Na and B both are decreasing and C is increasing. Acha, these changes. Any idea about Ga bar, Gb bar, Gc bar? Say, suppose there is a Ga bar, Gb bar, Gc bar here. And Ga bar, Gb bar, Gc bar is here also the same. Na and B and C different. It is understood. Very easy to understand. G bar, Gb bar, Gc bar are the values that was here. Is it here also? Now your answer will be never, sir. Never. Not only these changes. If this change, G prime would change. But fact is, sir, if all change, why G bar is a function of composition, sir? Composition of G bar is Ga0 RTL and activity of A. Activity is mole fraction of A. Of course, gradually decreasing mole fraction of A, gradually decreasing mole fraction of B, gradually increasing mole fraction of C. So they are always manipulating, changing, modifying Ga bar, Gb bar, Gc bar, Na, Nb, and C. So new G's all the time is coming. Now I tell you in context, I may forget so many things to say. That these minimization. So what what they are considering, if you are giving this problem, so 1 mole, 2 mole B, 1 mole of A, 2 moles of B, I have started with what is the equilibrium composition? Tell me, given temperature 1000 Kelvin, given pressure 2 atmosphere or maybe 1 atmosphere, if you like this. Answer. So you actually normally you will not find the equilibrium composition. This point, not by the, who will draw the graph? We are not going to draw that. This is for presentation, understanding. This happens there. But we will solve the problem through delta G is 0 today. Delta G is 0 the equilibrium condition. We'll find out this actually. Okay, and through this relationship, I'll take up equilibrium condition. This is actually called classical method. So I'm coming to this. So equilibrium state calculation, 2 ways. Equilibrium state, very important. What is the equilibrium state? Equilibrium state calculation. Finding the equilibrium state calculation. 2 ways, right? 2 ways, clearly write 2 ways. 2 clear ways. to have bigger, actually, so two clear ways, sequential calculation, two different ways, two ways, two ways, calculation, two ways. One is, I'm telling you, one is finding delta G is 0. Equilibrium, I'm not writing all the time. The 0 means equilibrium, less than 0 is spontaneous. It takes time. Delta G is 0, 1. This is called classical approach. And second is what? Tell me. What is the other name of this? Tell me. dg prime pt by dn is 0, which means at the same breath you say g prime pt is minimum. Just say g prime pt is minimum at the equilibrium state. So find when g prime pt is minimum. That means every point you can do yourself. Every point you are taking these values, you can do yourself, at least mental calculations, mental exercise. So these are, if you know activities, partial pressures, mole fraction pressure, all known, sir. At certain value, I will choose, okay, sir. Choose, sir, 0.1 has converted A. Obviously, what are the values? Come easily. So 1 it was, now it is point, I'm sorry, 0.1 means 0.9 now currently, 0.1 gone. It was 2, say, for easy, 1.8, etc. At 3, so and GA bar is what you may argue, sir, GA bar, how shall I get, sir, NA GA bar? GA bar, sir, GA 0 plus activity, activity means gas partial pressure. I wrote now, partial pressure. Achha, did I finish that though? Nitrogen Pi0 is 1. So that means activity is partial pressure. So partial pressure is a mole fraction time total pressure known, moles known, everything known. But GA0 is the bottleneck. So GA0, sir, who will give us GA0? Actually, I tell you, delta G0 through this famous relation has been measured by number of great men and tabulated delta G0. What we will do now, suppose delta G0 is known, then there is a practice, will actually protect this, or will defend this delta G0 value. How? I will consider the delta G0 turns out to be minus 40 at the given temperature from the book, data book. I have data book also, I can show you, and you take a problem. Minus 40, then we consider what, consider this is GA0 is 0, this is 0, delta G product minus delta, give the product as minus 40. So everyone is assigned absolute value by trick. Protecting delta G0 is minus 40. You can consider 2, 3 and 40 means 45. Like this, okay? That is possible. So delta G0 is minus 40 cannot be violated. So this is protected. So GA0, GB0, GC0 obtainable. GA bar is J0, RTL and AI is partial pressure, mole fraction. So everything is known. So we can ourselves calculate this point, number of points until the whole range we calculate. Then we can see what is the minimum value. So 40, 30, 20, 10, G, 10, 10, 12, 20, 30, 40 again, then 10 may be the minimum point. So we can, but this is such a difficult exercise. After, if we do manually, so who does this? Computer. Software in 1 second, just by a click will tell you what is the equilibrium composition, means equilibrium number of moles. So this effort, this classical approach, this is called right here computational thermodynamics. Classical thermodynamics, classical approach, or like classical thermodynamics, computational thermodynamics. This is done by softwares. Uses softwares. Which softwares? I give you an outline of these softwares. Okay. Namely, few names. Paxage. Have you heard the name? Paxage. You will use this. Paxage. Thermocalc. Thermocalc is not so much for chemical metallurgy, for physical metallurgy, phase diagram. Thermocalc, but I am writing you. Another is my students in the lab did this with me, solver. Not so elaborate, but it is also helpful for this small scale calculation. Solver, okay, etc. There are many. I can. So they can give the answers. So this is the minimum method. And delta G method we will solve today. All problems that we will solve, we will not use computer here, but this you have understood. Next partition question is, sir, now take up this problem. Can I remove this thing I can remove? So I should remove this, okay? Delta G is 0. So please let me write this. I am telling you. Now 1 to 2 delta G. Delta G. So let us, now answer is, I am giving the answer, confused. Answer delta G, yes. Now I agree. That should be also considered 1 to 2. Right? So this state to this state, this state to that state, this state to this state, this state to that state. So do this, and what is the, will you consider delta GPT less than 0 is the spontaneous criterion? This is the question. So question. So in other, so I am removing this. This is maybe the an important thing. Question. Can, I have to write on the top. There is no way. I remove this. Actually, they are so important. Which shall remove? I do not know. I am removing this. Yes. Question continued. Or more direct question. Can delta G pretty be considered be considered as a criterion? As a criterion for spontaneity, I am asking. Of spontaneity? Guess, like delta G prime PT is negative. See, have you noted this? See how actually is negative value, sir? Why not, sir? 1 to 2. But you say, sir, I have started with something, sir. 2, how shall I know? I want whether reaction will occur, then if it occurs, then go to the 2. Question is main question. But even so, if you say, sir, if it is actually 1 to 2 is conceptually is negative, the here answer is question, can you say like that? Answer not always. That's why we will not use with Gaussian. I'll explain this. Please say I assign a value and you don't mind at all, I guess. P, since I have considered P, what is the, I write here, say 50. Means joule. What is the joule? What are the equilibrium state? What is the minimum? Give assign a certain value 20. 20 joule. I am write separately. R is what? Tell me. It is going up, means maybe draw this maybe 30 joule, na? 30. Not bad. Joules. Now see, tell me whether the reaction, answer this question first before I writing. I will write P to Q, state 1 to state 2, our first law of thermodynamics application. 1 to 2, delta G prime PT, because it is G prime PT, delta G prime PT, or if I say delta G prime or delta G, from 1 to 2 is how much? G2 my final minus initial. What it is? 20 minus 50 minus 30, negative. Sir, why is it good? Sir, yes, spontaneous. It will go spontaneously, obviously, and of course good. Why you say doubt? You are a doubtful person always. Okay, skeptical. But very good. I am asking. Next question. I am again considering P to R. 50. And final state is R is what? 30. So again final minus initial, 30 minus 20, again negative. So that means system can move from this to R, starting. Oh no. Then why is the universality of this? That means how long it will work? Until equilibrium. Who knows? So it is not very sure, not conformity test. Only so you have to calculate equilibrium. Yes, one problem I will solve. Very nice problem. That also later. Then I will show you that I can give you certain composition. I will give you a composition after this composition. You don't know what composition it is. So you have to verify whether it is past equilibrium. Past equilibrium delta G prime PT may be negative. Still reaction will not possible, because why not possible? Because reaction will get stuck here. Stop here. This is the answer. So can I write this in a few sentences? So answer, as I'm writing, and just short answer. So write, let P is of hot joule, 50 joule. Quickly, 50 joule. Q of hot value, 30 joule. Oh, sorry, 20 joule. And R, 30 joule. Now quickly say delta G P2Q. P2Q have concept. It can be from the very beginning also, anywhere to anywhere. P2Q is what? Tell me. Delta G prime. Acha, you should write what? What I am considering. Now, please note. So many things to note. P2, what to what? Tell me P2Q. What you write? G prime Q minus G prime P. Happy? What it is? G prime Q is what? Tell me Q is 20 minus 50 is minus 30 joule, and it is negative, and the reaction is also spontaneous. As we see, it is also spontaneous. Also spontaneous is also spontaneous. As we see, you see means write this quickly. But give a but, huge but but delta G prime PT to P2R. P2R, tell me R is what? 30. 30 minus 50 is minus 20 joule. Negative, however, negative, I should write here negative, but this process not possible. But this process not possible, impossible. This process is impossible. Impossible. Right? Nicely right. Sorry, I didn't want to disturb. Very good. Very good. Impossible. So, because this is the trouble. One thing have you noted? I said previously what? You read what I said previously. Criterion is what? So far we have used at a given state. What is the condition? I will use delta G less than 0 for spontaneity. Delta G is 0. Delta G. This is what? G prime PT. Delta G prime. This delta G is actually from between state to state. G prime minus okay, this can be delta G prime. Is it? Nah, this thing is PT means this along according to this graph means one point to another point on this. This is delta G here. G of products minus react at a state. So careful, delta G, delta. This is one important thing. Okay, this is not very clear in the books. Okay, what is the criterion, sir? I say what is the criterion? First criterion, second law. Ask second law. No one else. Ask no one else. Second law says this, from which you can get this easily. From which you get it is nothing but delta G from this relation, which have removed, not removed. Delta G. So this is the criterion. Delta G, sir, at a state. That is also not written. So delta G state. Oh, don't worry. But it is delta. It is state to state. It's state to state. But state to, we have to treat with caution. So we have to be. So this fails. So here delta G prime PT as criterion fails. Write this. At least write this as criterion fails. Sometimes works, sometimes does not work, fails. Because that means we have to be cautious with before equilibrium. So before equilibrium, before the, so write this. I write here one line. No, it may be noted at least. I do not know what I am doing. So, may be noted. It may be noted. Delta G prime PT. Sorry. Delta G prime PT is negative will serve as a criterion. May serve as a criterion. Will serve as a criterion. As a criterion for what? Tell me. Criterion for spontaneity. For spontaneity. How long? Which domain? Until before. That's it. We'll use this also later, but that is the before equilibrium. Everything. This is over. This part is over. So next is this part. This confusion parts are over. Quickly, I will not spend more time on this. I will take up some other things quickly. Now I tell you what is delta G. Next, next discussion. Next part. Next. Another point. Next. What is delta G? Note, delta G is 3 GC bar minus GA bar plus 2 GB bar. Now, see, this delta G negative decides that reaction will occur, reaction will move. That means these are responsible. These are very important stuff. Hence, they decide whether reaction will flow, move. Like pressure dictates whether a gas will expand from high to pressure value. So pressure is called, what you call this, I am not writing. Pressure is called mechanical potential. So you have mechanical work done. If it is high pressure to low pressure, so mechanical potential. If it is temperature, high temperature to low temperature, heat flows. So temperature will be maybe called as a thermal potential. And if it is height, then you know whether height actually, if gravitational work can be done from level, from greater height to lower height. This we can get this. Actually, gravitational work can be done, or things will move under gravitational field. So this height would be called gravitational potential. All are potential then. These are deciding. So lower to higher, no, it will not move automatically. So these are potential. So since this decides the value of chemical reaction, so there should be a kind of potential. What potential they can be? Chemical potential. This is chemical potential. So these are all chemical potential. Generic symbol is mu. So right, GI. So GI, all GI bars. What is the definition? I am writing once more for you. You can help me. What is GI bar? Anytime del G prime. Tell me del Ni, constant pressure. As you know, that it can never be changed. If I often change, then you will not study. No one will study GI bar. Is mu I. This is your chemical potential. All. So mu I means this is mu A, mu B, mu C. Okay, this is chemical potential. So this is another thing that I wanted to tell you. Another thing I tell you. Achha, if you, I will not discuss much, but I give the results. These can be plotted. Suppose next question, I start with a leading question. Then that will help us to. I can remove all these things. Okay. I am removing all these things. Top 3 maybe written. Top 3 maybe remove all these things. Suppose next question. Suppose we are carrying out a reaction. In a constant volume, constant temperature system. Follow this. Temperature system. Constant volume, constant temperature system. So, can we apply system? Can we still apply delta G? I'm now over. Delta G prime PT I am not going to use. Delta G at a given state, reaction will occur or not. Can we still apply delta G being negative as a criterion, as a criterion for spontaneity? Of spontaneity. This is our question. I am sketching you. I am carrying out a metallurgical blast furnace type reaction. CO plus half O2 is my chosen reactions. I have taken certain number of moles, etc., etc. NCO, NO2, don't understood. These are taken. This is a constant volume, unlike constant pressure. And constant means thermostated. So far we have discussed what system? constant dgpt, constant pressure, constant temperature on the top. Then I have done the whole development based on that. If it is vt, sir, can I apply Gibbs energy? For constant v, constant t, another function is very popular or well known. Who is that? Helmholtz free energy. Remember the criterion of spontaneity? Yeah. Criterion. Let me remove this first of all. Then I will tell you quickly. Write that. Never forget. Few things you will never forget. That is, this criterion. Criterion. Okay. Second law. Second law statements. Second law statements. Uh, Tell me dgpt. ds universe I am not writing. Dgpt less than equals to 0. I am writing minus d double prime. I am not writing. That is many times discussed. Next is vt. Who is the suitable function? Oh my, dA, Helmholtz free energy. dA vt is less than equals to 0. Still, and next is enthalpy as sp less than equals to 0. Internal energy can be a criterion less than 0, and entropy we call. And I'm drawing a line. Entropy is not energy. Drawing a line. ds uv greater than, this is greater than, entropy increases for spontaneous process. This decreases. Okay. Remember again at this time, since in case you forget, you never forget this one. dg is vdp minus sdt. dA is minus pdv minus sdt. dH is tds. From this it is, these are coming vdp and du tds minus pdv, and you may write, if I may write, okay, ds is 1 by t du plus p by t dv. You may write this way also for ds. So these are the choices. Okay, this you know. So since constant volume, constant temperature, I can use this, and I will soon, okay, very quickly the similar diagram. And then I will show why we are not using. No books are using, but they should be equally competent. None will use. Only one and one Gibbs energy. After entropy, next Gibbs energy. These are all academic. These academic, as enthalpy is very important, but that is not as constant entropy, constant pressure. This is very difficult constants. Okay, enthalpy, constant pressure, constant temperature. We have used already. Full thermochemistry. Not that. This is a criterion. This is a criterion. These criterion will not use, useless. Only top one. Okay, I told you when I was teaching that only one is actually okay. Maxwell relations, perhaps I remember. Answer is, can I apply? Yes, we can still apply delta G. Yes, we can. Question two, can we apply? We are carrying out. Can we still apply? Answer. Yes, we can apply. We can. Yes, we can apply. What is apply, sir? Why this? Now follow this. This is interesting. So delta G, the way I am, what is delta G? The reaction at a state. At a state. So you know what has happened. You know. Yes, you have 1 mole, half moles you have taken, and they are reacting. The same thing is happening. It decreasing, increasing, and perhaps it will stop in the middle, which is called equilibrium. This is the whole story, nothing else. So delta G at any composition, we are wondering, okay, whether reaction will occur. Just pick up any composition, that will be your problem actually, whether reaction will occur. So delta G at a given state, sir, what is constant pressure? What is constant temperature? What is constant volume? So we don't understand, sir. This thing we don't understand. Constant pressure, this state to that state under constant pressure, this state to that state constant temperature. This is understandable, sir. Constant volume, constant pressure, you have got this. But what is the at a state, sir? Who changes? At a state, change is about one state to another. So when it is moving, so this is moving CO2, half O2, so midway, sir, that state, that point. Of course, you see here pressure will change. Pressure, your starting pressure is 1 atmosphere, sir. All together 1 atmosphere. Why it will change? Yes, as the reaction progress, I cannot write so many things. If the reaction progress, pressure will do what? So I start with 1 atmosphere, say. Then pressure will remain 1 atmosphere. See? No, sir. 1.5 mole giving to 1 mole. Means moles decreases in a constant volume means pressure decreases. So 1 atmosphere, so it is never a constant pressure. But we will use free energy because it is pertinent to on any state, and there what is the constant, that value is that value, that pressure, that temperature. Okay, we don't have to that at a given. So at a state we are not concerned about constant pressure or constant temperature, constant, yeah, even. And can you give an example? This is where pressure changes. Can you give another example? Just here also temperature may change. Yes, yes. Okay, but exothermic endothermic we carried out in thermostat. Heat temperature does not change. Thermostat purpose is temperature constant. The heat is either extracted, it is taken up or released. So temperature does not change. So you are close. So what system that should be? Isolated system, because heat will not be coming out, so heat will heat up and temperature will rise. So temperature rise, even there let the temperature rise. I started with say 500 Kelvin. So in then that time, what is that system? Since I'm drawing that, this should be like this. I'm drawing here. This is constant rule. And what is that? I'm not. This will be what? Nothing but the similar constant U, constant V. Bomb calorimeter. Constant. Yeah. This is isolated system. Take it right here. CO plus half O2. Yes, sir. Okay. What is what are going to write? CO plus half O2. What is isolated system? And this is constant T, constant V system. Okay, don't do it. That means again their temperature rise. Let it be. Let it rise. They at a state that has not any compulsion or any dependence on this temperature remaining same or temperature changing. Okay, that means at any state temperature is that temperature. Next state temperature different, but at a state, since we are judging at a given state, so whether temperature rises or decreases has no concern. Okay, about the application of delta G, has no will not actually affect the use of delta G as a criterion of spontaneity as applied to a given state. So write this. So answer is this. Answer is this. The answer continued. Answer continued. Answer continued. At a given state in which you apply, at which you apply delta G as a criterion, at which apply delta G being negative, delta G being negative as a criterion, the question of constant T or constant V or constant P meaningless. That's why meaningless, sir. Meaningless. Because at a state, only one value. Because variation in T, P or V, or or V is pertinent, is relevant when we are talking of two states. When we consider two states. Two states. Okay, that's it. I think this is understood. Like state 1 to state 2. And where I use this? Where I use this a moment ago? Delta G prime PT. There 1 to 2 we can apply. So there you will apply. There, okay. So that is not delta G. So this part is over. Quickly before leaving this, okay, this okay, over. Suppose still we know these are for academic purpose. Not practical, not useful. Academics, this is solely, this solely is useful. This is one question. Why always PNG? Why not? So many things were there. Have you considered this? Okay. This I will not tell you that certain. Okay, I tell you, entropy should not be ignored. Can you tell me why? The entropy of the universe, it cannot any process, you cannot ignore. Why? Because entropy of the universe you should not ignore, because this comes from where? Entropy of the universe. So when it says continuous process means entropy of the universe must be increasing. When it says reversible entropy of the universe, so it cannot be. That is, then you have to consider system and surrounding together. But it is about system alone. So, but see the difference. But entropy cannot be, which is derived from entropy. Okay. Achha, next time actually telling you, suppose just for exercise, suppose although not useful, we want to draw a plot of A prime TV versus N for same reaction. For the reaction, CO plus half O2 is A plus 2B is 3C. Na? I drew na? A plus 2B is 3C. Carried out in a constant volume, constant temperature reactor, constant volume closed reactor, closed system, closed reactor. Just I am drawing this. Actually, I will not extend this because these are not useful. But just in case you might, some will tell you that these are similar thing. Similar thing. See, you can do this. Now, then last after this, I will give you why Gibbs energy. Main reason why Gibbs energy is useful. Others are useless. Maybe you can call it useless. But for academic interest. It looks very small. Okay.
Yes, sir. The reaction is not the writing is not.
This is not easy. It's not really available. Acha, it's okay. Leave it. I don't write. Don't. I'll show this main thing here. I'm drawing it. Acha, remember. I will remember this. Acha, I'm drawing similar way. TV constant. Same way. Acha, before this A instead of G A prime TV. Here also similar thing will happen. Okay. A plus 2B 3C. Same. Okay. This can be done. Okay. This now so it is equilibrium, right? It is minimum. This is equilibrium. How will you proceed? How will you proceed? Here why this the same way you proceed. How you proceeded there last time? In case of this energy, what is the starting line you wrote? That dg prime is pt. You wrote perhaps, or g prime is a function of starting line. Here a prime start. How will you start? A prime is a function of, tell me, temperature, natural choice, volume. Okay, N1 I'm writing N1, N2, N3 or Nij, what I wrote? NC. Acha. Na. Just I'll give dot etc. Da prime. What will similar? Del A prime by del T. V etc. Na. dt. Acha, Na, right? First term NB, NC. Da prime dt. dp. V. dp is what? dv. d prime dv. Temperature Na, Nb, Nc, dv plus next tell me what? Da prime. One case I am showing Da prime. What tell me? DNA. Temperature, volume, Nb, Nc. I am not writing. Plus I am giving. You know the rest. What it is this? Can anyone remember? What is Da prime with this one? Da is minus PdB minus SDT. So this must be minus SDT. This is must be minus P. Da prime minus PdB. A moment I wrote, I remove this. Da prime is, Da is what? Minus PdB minus natural choice is P, B and T. Minus S. So this must be SDT minus S. So you write Da prime what under constant temperature volume that you are interested? So first two terms drops like last time, and what you are getting? This is known as what? Good boy. A bar. Sorry, unfortunately, G a bar. G a bar. G to is unfortunately, but I cannot help. A bar. Maybe another one, right? Then in that case, dA prime by dNB. Temperature, volume, Na, Nc. This is what? dNB plus. This is G at A B bar. You understand? So what you are getting? Right? A bar DNA plus A B bar dNB plus A C bar dNC. Similarly, remember minus DNA, that logic you apply. If you apply that logic, you will get 3 AC bar minus A bar plus 2 AB bar. Okay, A plus 2 B na? This you will get times dN like this. This is known as delta A. Delta A, and dN is non-zero. Huh? A plus 2B is 3C. Yes, question. Minus. Yes, dt is 0. Under constant temperature. Like it gives energy under constant pressure and temperature. So this term drops. S does not drop. dt is okay. This one. So a similar approach. So what you are getting? Remember, delta A dN C. Teacher, compare. Analogy. dg prime Tp is what? Delta G dN. Recall, I written there also. Up. So you can do yourself here also. Similar things will happen. Then sir, everything is good. Then why you are saying bad? Like this. But why you are not using? This is the maybe the last point. Why you are not using these 3 points? I will tell you why. This is one question that you should be careful. Why people not use other? Acha, before I consider question. Constant temperature, constant volume. Which one?
No, sir. Why did you cancel the first term?
Like under constant temperature and constant volume. Constant this constant temperature. This he did in the previous case also. Similar one-to-one correspondence. You can very easily. Now, still another one. I'm showing. Still another one. Can you tell me if you start here? Actually, there is some difficulty to understanding. See, this equilibrium and the equilibrium, previous equilibrium, same equilibrium. This equilibrium and that previous equilibrium are the same equilibrium. Now, see, in this case also same number of moles has been happens to be, but actually suppose CO plus half O2 is CO2. Tell me, I consider this one for free energy and what is called Helmholtz free energy, gives free energy, and again minima. So this is equilibrium for this system, for this constant volume, constant temperature system, and their constant pressure, constant temperature. Do you think the same equilibrium? Think about this. No, it cannot be same. Why, sir? In constant volume, constant temperature, pressure is changing. It was all along that same starting pressure. So, if the state pressure changes, state is different. Okay. Are Baba, constant volume, constant temperature. What happens? Temperature is same. Constant, easy way. Constant volume means what? Pressure decreases. I start with 1 atmosphere. What is the equilibrium one? At least less than that, because equilibrium is a certain extent of transformation, and during that time 1 atmosphere has decreased to certain pressure. So it is no more 1. That means this state is not described by 1 atmosphere pressure anymore. But in the case of temperature pressure, what is the pressure? Unchanged. So 1 atmosphere. So you can say this equilibrium, that equilibrium not same. Don't think that is depends on what system you are working. Okay. And similarly, still another one, entropy. This is also helpful for you. Entropy criterion is what? Entropy criterion, tell me. Entropy criterion. You can use that. Very good. Right? That constant U, constant V, isolated system actually, and no non-mechanical work. See, here I have not written. In all this temperature pressure that keeps energy. All along I have not missed one thing. Here I am writing so many things. dW prime is 0. No non-mechanical work. Okay, see my point. So quickly, entropy. Can you tell me again? Say what is the reaction? A plus 2B, 3C. How to start? Tell me. This time, greater than 0. Yeah, so entropy, this is the equilibrium and this is the maximum also. So see, so many curves, okay? Equilibrium is given by this. Okay. Do you need water? It's okay. Okay. So maximum. This is again equilibrium. Now again I will ask this question. I start with the same state. I am trying this curve, means temperature volume system, constant temperature, constant pressure for Gibbs energy for Helmholtz, and now constant energy, constant volume for isolated system. And every time I got an equilibrium, minimum, maximum. The same state, same equilibrium here. Guess, see the system. If compared with the constant pressure, constant temperature, what happens? Constant pressure, constant temperature means the equilibrium state has the same temperature as the initial state. Say 500 Kelvin, namely. What is the temperature? It starts with 500 Kelvin here also, and then it is a bomb calorimeter system, thermoflux system. Okay, 500 Kelvin remain 500. If it is either exothermic or endothermic, suppose this is the reaction. This is actually CO plus half O2 is CO2. I wrote this, but if you have to consider this, this is exothermic reaction, I know. So heat will come out. What will happen? The temperature, when equilibrium is say all of them checking, equilibrium will reach with different temperature. So that equilibrium state can never be same as the constant P, constant temperature Gibbs energy equilibrium state, neither equal to Helmholtz energy. This is actually our understanding. So last thing in this case, I'll tell you why I'm writing this topic. Perhaps authors actually avoid perhaps why the Gibbs energy, why the Gibbs energy is, why is the Gibbs energy alone used in the equilibrium calculation, in the chemical equilibrium calculations, in the chemical equilibrium alone, not other functions, like alone. Write this, remove this, not other functions like, tell me, A, U, H, okay, erase, okay, H I'm writing, are not used in the chemical reaction criterion, chemical reaction equilibrium calculations. Answer I am giving you point wise. First point is what? You write this. Answer this. There is no answer. There is no analog of this in Helmholtz energy, enthalpy, and what is this called? Okay, right. AUH also SU right also. There is no analogs. There is no analogs in the relations involving AUHS analogs of the following reaction, of the following relations. In the relation, in terms of there's no analogs in terms of is of the following relations. Write this, maybe of the following relations. What are the relations? Of the following relations. What are the following relations? Write this one by one. First we write this, dg is RT/lnf. Who will give us? There is no dA and dAE, etc. No, only dg. This leads to what? You know, remember yesterday and today also, gi bar minus gi0 is RT/ln activity. What do you get? And still you proceed, then you write delta G is delta G0 plus RTLN Q, and also write delta G0 is minus RTLN K. So we cannot have, because this beginning is, this is starting is this, we don't have dA, we cannot have this, okay? Okay. See from this, okay? RTLN K is the thermodynamic equilibrium constant. Remember last I told you, K is the analogues in terms of AUG of the following relation. You cannot, so that's why you will always get delta G0 in standard textbook. Delta G0 data tabulated, not delta A0, delta A0 means, okay, the way I have defined here, okay, this one. This you will not get. Delta H0 is giving, that is different delta H0, actually standard state, but this is this is actually in the form of A plus BT is tabulated. So not delta H0 or delta U0 or like this, okay? Delta H0 I tell you, but delta H, there's a relation between this delta H0 and equilibrium constant. So you cannot relate this equilibrium constant, you cannot calculate, so you cannot determine the equilibrium, okay? So okay, and okay, this fine. This you will understand. No analog for this. Fine. So this part is over. So let us take up some. Let us take up some problems we will actually solve now. Starting this form. Remove all these things. Over. Nothing else. Satisfactory discussion. What is this called? Okay, problems. Numerical problems. Example problems. Example means I am exercise I'll give you, but as assignment, but that also I'll solve here. But example problems. Problem 1, easiest. See, what you have learned so far, you will try to utilize this quickly. Easiest I start with, find, sorry, find if the metal M, find, okay, find, question, problem 1, find if the metal M will be oxidized to MO2, will oxidize to MO2 solid. You can write here solid, metal M, write in bracket solid for description. In an 1:1 oxygen is to argon mixture, happy, at 1000 Kelvin. Very easy question. At 1000 Kelvin and 1 atmospheric total pressure. This is the question. Answer, solution. I should write on the top. What I'll write on the top? Tell me. Delta G is delta G0 RTLN Q. This I will not disturb throughout. And what? Delta G0 is minus RTLN K. And what? Q less than K. Okay. And delta G negative. Negative is, what is this? 0. So I am very sorry. Criterion of spontaneity, right? Less than spontaneity equals equilibrium. And also Q less than K, that is delta G, or from here Q less than K, less than equal to. This means this I discussed. Start. So what to do, or given data, I consider the reaction. M solid, consider the pertinent reaction, consider the relevant reaction or pertinent reaction. What is the reaction? Metal solid plus O2 gas goes to MO2 solid. Now, given this delta G0 will be given. Delta G0, as I told you, delta G0 is tabulated. Delta G0 is stability, and delta 0 can be linked up to equilibrium constant, hence equilibrium. Delta H0 is a segment of it, okay? So that cannot. Delta G0 is minus 60,000 plus 100T, okay, 50T, 50T. Joule. This is the data given to you. Solve the problem, okay? So what you know very well what you have to do to check whether Q less than K, or alternatively delta G less than K, whichever you will like. There are many. So I start, what is the delta G solution? I do one thing, delta apply delta G0 at 1000 Kelvin. Oh, shall I should have sketched this. Always sketch the problem. You have a metal powder sitting here, metal solid is flowing into this oxygen argon mixture 1:1. Open to atmosphere means 1 atmosphere total. Open to atmosphere, what implying P total is 1 atmosphere. The system is under 1 atmosphere. This is the meaning. So delta G 1000 first time calculated, for some reason you follow me because you are beginners. Minus 1600 plus 50 is minus 10,000. Now that does not waste time. Since beginning, quickly 60,000 plus 50 times 1000. Temperature being 1000 Kelvin, so minus 10,000. 10,000, from which I will teach you how to get the equilibrium constant. You are feeling unwell. Delta G0, you want to go to the toilet? You want to bathroom? Delta G0 is minus joule, unit, mass, unit. Delta G0 is minus RTL and K. Happy? RTL and K, delta G0 1000 here. Delta is minus RTL and K. Apply this, I say every day 10 times. Okay, let us see how many times today. Delta G0, what it is? 1000. Okay, you write this. Delta is actually this. This is this. Right, 1000. Tag 1000. Delta G0 is a function of temperature. So if I missed any points, I will fill this in here while discussing. Delta G0 is a function of temperature alone. Right here, note this. Note here. Note. Maybe I will tell you later. Delta G0 is function of temperature alone. Let us see if you can answer this. Yes, sir. Function of temperature alone. What does why, sir? Delta G0 is, after all, standard state energy change. Means, what is the meaning of delta G here? Tell me. Standard energy of this 1 mole minus standard energy of 1 mole minus standard energy of 1 mole O2. So why this is function of temperature alone? And showing also temperature alone. Why? For the fundamental definition of standard state. What is the standard state? Sir, pure state, 1 atmosphere, these are bound. This cannot be changed as a temperature of interest. So temperature dependent. It can be had time. So that's the function of temperature alone. Also it can be shown. This I'll show you. This function of temperature alone is okay. Minus. So what is this value? Minus, quickly. This is all right. Minus 10,000 is minus 8.314. What is the temperature? Substitute. Now you proceed with me. Ln K, or K will turn out as ln K. See, K tag always temperature. K is likewise function of temperature alone, right? K is also likewise. Note this. This is noting I will discuss many times later. Function of temperature alone. Likewise, note. Anyway, K thousands. That's why we tag this. May not tag. It will imply the 1000 Kelvin you are discussing. What is this value? You will do these calculations. You do yourself, and I do myself. Okay, this is what 3.33. 3.33. Okay, what is the Q? Remove this. Now complete this problem. What is Q? Q less than K. I have written somewhere. Q less than K means spontaneous. Q is K means state of equilibrium, and Q greater than K means impossible. So Q is what? Tell me. K is this. Q is what? Q is quotient. Activity of the product same as equilibrium constant. Equilibrium constant is also they are actually the same ratio, similar ratio. One is pertaining to equilibrium, another is pertaining to the actual state under study. This is a state under study. This refers to Q. This will be utilized in Q. So you write this activity of the way you see the activity of M, write activity always, starting line. And what you write? Q as write state under study. State under study, another thing I will write, that you may write state under study, or you write actual, or write actual, you write as different from K, right here, as different from equivalent K. K is again same similar, right? AMO2, right? Similarly, exactly similarly. What you write here? Not actual, but equilibrium. It is thermodynamic equilibrium constant. Thermodynamic equilibrium constant. Okay, happy? So let's leave aside all these things. Okay. So Q is what? It is what? Tell me. Here in the present case, see what are here. M is there, and what is coming over it when the reaction takes place? Oxygen argon mixture. So what is the simplify? MO2 here actually little bit catch is there. MO2 is not there, but present MO2 will be produced pure. Present, it may be present. If it is present, you check. If it is present, if the reaction occurs. If it is absent, the reaction will all the more occur. So presence you will consider, means it will be produced pure. I write that. So is 1. It is better right here. Right? Why I like that? Activity of M is C. Tell me why activity of M is what? Tell me. What is the activity of M? 1. Pure is 1. 1. What is the activity of O2? O2, tell me the first thing what I took. Partial pressure oxygen. Step by step. So 1 by PO2. PO2 actual. I will explain this. I will explain the left hand side. MO2, why? MO2 was not present. Still you are considering, sir. If it is not present. Actually, another thing I tell you. MO2, this is very, to convince you nothing else. Achha, tell me. Activity of this MO2 also, this is chalk. What is the activity of this chalk? Pure chalk, say. 1. So I just broke it. What is the activity of this? This whole thing 1 activity. This, what is the activity? Still I have reducing the size. That means it doesn't depend on the amount, mass. This, but further, then actually suppose I have some, this, what is the activity of these powders? 1. That means amount does not change. Now when it is not there, what is the activity? This is for fun. This is for fun. What is the activity? No, you still, no, that you, I tell you, that you don't say. Since the amount changes, it does not change. So when it is not there, it is still 1. It is one way of understanding. Best I write here that it will be produced pure. The more you will learn by experience, okay, or thinking. Another thing I am giving. Density of this water, I have seen water under somewhat here with you. This, what is the density of this water? Hold it. What is the density of this water?
1 gram per ml.
1 gram per cc. Now ml. Okay. I reduce this to 50% of this. Half of this. What is the activity? 1 drop of this. What is density? And there is no water. Water is not there. What is the density of water?
1.
Density of water, you say, will say no, what, there must be some water to tell that density is 1. No, density of water is 1, so always, whether it is present or not. That means it is present. This is an analogy. So when it is absent, what is still density of water is 1. No water, density of water is 1. So this is this type of analogy I am giving, so to convince you that it will be produced, and I like that. Actually, 1 by PO2. Tell me what is the value? 1 by PO2 actual? What is the actual? Look at the problem. Look at the condition, experimental condition. What is the PO2? PO2 is what I told you. Mole fraction times total pressure. Total pressure is 1. So you can write this XO2 times P total. What is XO2? 1:1. 1:1 means what? 1 by 2. Half. That is 0.5 times 1. Okay. So 1 by 0.5 means how much? Write this. Actually, write this underneath. 2. Please tell me. I'll explain the same. Here I am writing. Hence Q, which is 2, which is 2 less than K, which is 3.33. So reaction spontaneous. So the reaction will occur. So the reaction will be spontaneous, means reaction will occur. If the material will oxidize, so reaction will occur means, so the oxidation will occur. So the oxidation will occur. Answer. This you have solved. Okay. Now here I write here. Note This is something important. Note MO2 will be produced, MO2 solid will be produced pure. Is not there, will be produced, wherever it is produced, produced pure. So will be produced pure. This is the argument. Hence, activity of MO2, which is not there though, but if the moment it produce little bit, 1, okay, is 1. Moreover, see, little bit produce, just 1 grain produce, but you have to check actually, okay, whether it will be, the experiment continue. Over, this is over. Now, you, what is the alternative? What is the alternative? This Q less than K. What is the alternative? Delta G less than 0. So that you try, since it is the first problem. Can you remove this? You try. Achha, Q is there, no? Q is to remember, alternative. Alternative method, not missing. Another problem maybe. Alternative method is quickly. Delta G is what? Tell me what is the link? Delta G is delta G0 plus RT ln Q. Cool. You set that value minus 60,000, right? This. What is this value? Minus 10, 50 T. Plus 50 T. So T is how much? 1000 plus RT 8.314. 1000 ln Q is how much? 2. Q is already done. 2. If you do this, see all numbers, you will get the value of delta T. You try yourself.